Thanks, Bill. I'm Bill. I'm one of Zach's students. I'm also probably the main maintainer of the FPBench standards and the specifically the FPBench tools as well. Give me one sec. So we're going to talk about FPBench 2.0, but first, is this going to work? There we go. Let's just take a second to recap the history of FPCore and talk about FPCore 1.2, the thing that preceded it. So FPCore, I think, has been a great success. The certain features of the language have been really useful in some applications. Specifically, it's unambiguous, really crisp semantics for describing exactly what goes on in numerical computations. And then also the fact that it has very flexible, extensible support for lots of different number systems. So this is great if you have applications that do weird stuff with IEEE 754 rounding modes. It's good for describing precision or format specific computations in a platform independent way. It's great if you just have some specific computation and then maybe you have a tool that transforms it into a different version of the computation and you want to tell users exactly what to do. So one example that I always like to go back to is this wiggly function from the Precomonius paper. The idea is that we have this crazy looking thing and we want to take the arc length. So you can do this with a pretty small piece of C code. It actually translates very nicely into FPCore. And then the cool thing is that once you have it in FPCore, you can go and plug in all kinds of weird number systems and weird precisions, and then you can make very cool graphs like this sweep, where I've actually changed the precision of the number system and then the number of iterations we do in the algorithm, and we can get this really cool visualization of like the trade-offs between accuracy and the numerical approximation that we're using. Right. So FPCore is great. With all those good things said, there are some major problems with the standard. Mostly they manifest as missing features. So the first one is that FPCore has no support for data structures. If you have multiple values, you need to make multiple variables. And then if you want to refer to them programmatically, the only thing you can do is an if statement, which is very cumbersome. And then as a sort of more minor point, it's also not composable at all. So if you have a large application, it's hard to implement it nicely because you need to inline everything. So you can kind of work around this. Like here, for example, is a dot product for 2 element vectors where you've just manually expanded out the vectors into individual variables. But this really doesn't scale. Here's like a 100 element dot product. And you can imagine how miserable it would be trying to do this for like 100 by 100 matrix multiply. And of course, keep in mind that 100 isn't even a very big number. So with FPCore 2.0, we want to fix that. We just add tensors to the language. I'll give a little bit of an overview here of sort of the design process. There's a lot more documentation about this and also like runnable code examples that you can run yourself if you go on the FPCore website and you look at the link by the standard. So just it is very high level. We sort of went with a minimal aesthetic here. In keeping with the rest of FPCore and with the idea that FPCore is a sort of mathematical description of a computation. So tensors are just going to be pure functional data structures. This should also be good for program analysis and make it easier for implementers. At the same time, we need to make this implementation actually usable for writing code. Some people, like me, write FPCore as source to implement applications or to port benchmarks. So we need to have the right set of iteration constructs and stuff to make common programs relatively easy to write. So I did a bunch of work figuring out how to make this happen very nicely in Titanic. You can ask me about my custom tensor Python library later. But so let's just go on and look at how this actually works in practice. So you can make tensor literals with the array operation, or like constructor, I guess. This is kind of like list in Racket or Scheme, although of course you can't modify the tensors once you've created them. You can't add elements or append to the list. Note that you can tell that FPCore is becoming a real programming language because you can finally implement Hello World. If you need more dimensions, you can nest arrays. So you might want something like a 2x2 identity matrix. And then if you want to use arrays, the only thing you can do is, well, you can ask for this number of dimensions and the size. And then if you want to actually operate on them, you have to get the elements out with ref, which is like, get an element of an array reference. And so, right. So that's great. It's not very interesting though, unless we can have dynamically sized tensors. So we have an operation to do that, which basically tabulates over the Cartesian product of a set of indices. This is called tensor. So here we'll have n rows by n columns, and then this is just going to make an identity matrix. We check if the rows and columns, the row and column indices are the same. Each of these body statements is going to be computed independently and then combined into the final tensor. We can also iterate over these things with basic for loops. The indices are going to be set up in exactly the same way, but then rather than computing independent body statements and putting it into a tensor, we just accumulate them together with a standard FPCore while loop body. So right, as I mentioned, we don't actually have any mathematical operations on tensors. Those are only over scalars. Fortunately, we can make our own tensor operations as FPCores because FPCores are now composable. So for example, here's matrix multiplication implemented as an FPCore finally. Note that we just put this identifier matmul after the opening FPCore statement, and then this identifier can be used for other FPCores in the same scope, the same way that you use a mathematical operation that's provided by the standard. And then if you look at the arguments, you can see that the tensor argument is just basically specified as a list. The first element is the name of the tensor, and then the other elements are going to be either fixed size integers, if we want fixed size dimensions, or variables, which will then be bound to the size of the particular input vector when we run the body of the FPCore. Right. So I'm obviously glossing over a whole bunch of little details here. If you need to use the standard, you can look at the documentation on the website. There's both a description and then also the design doc if you're more curious about the sort of process behind it and want to see more examples. So now that we have tensors in FPBench, what can we actually do with them? I'm going to talk a little bit. I'm going to give some very early results about a sort of prototype tool that I'm working on called QuantiFind. So QuantiFind, the idea is that we want to quantify the benefit of using specific customized number systems for particular applications. So if we have some set of applications, and then those applications provide accuracy measures, we can then also, if we implement those applications in FPCore, we can use another tool I built called Titanic to both run those applications on custom number systems, and then also get a sort of abstract cost metric of how many bits it cost, how expensive was it to run on that number system. And we can combine this together and basically search for a Pareto frontier of interesting configurations that have like the least abstract cost for different points in the accuracy or quality space for an application, right? So I'm just gonna zoom through some examples really quick here. I probably won't have time to fully explain this stuff. But so one application we might want to look at is dot product. Specifically, we might have say some low precision dot product, but we want to improve the precision by having a big fixed point accumulator that will prevent us from overflowing or rounding our intermediate accumulated result. So the question is, how many bits do we actually need for the accumulator? So here's a parameter sweep. We have 1,000 pairs of 1,000 element bfloat 16 vectors, uniform random between -1 and 1, and the x-axis shows different accumulator sizes, and then the y-axis shows the average number of ULPs across those 1,000 vectors. So if we have like a 10-bit accumulator, we have almost 10,000 ULPs on average, which is pretty bad. We don't get the exponent right. But then as we add bits to the accumulator, we can see on the Pareto frontier here that we basically keep almost linearly. Well, I mean, I have my janky log scale y-axis, so we basically linearly add bits that we get right. All the way down to we finally get the right answer for this particular input at 29 accumulator bits. So that's kind of boring. I didn't have any good pictures there. So let's do something a little bit more exciting. We can actually pretty easily now implement a Runge-Kutta stepper and use it to run the Lorentz equations. So I'll note that you don't actually need tensors for this, but it is really, really, really nice to have just 3 element vectors to represent 3D points. So here's a Pareto curve for that. Our y-axis, our horizontal axis is going to be the total bit cost for the computation. Note that under the hood, the search is actually optimizing independent sizes for like the different coefficients in the Runge-Kutta algorithm, and also like the total number of bits that we have when we evaluate the equation. And so if we have enough bits, somewhere between 10 or 8 and 12, depending on which coefficient it is, we can get this to work pretty much exactly like it would with doubles. And then as we start chopping bits off, we get increasingly broken looking Runge-Kutta Lorentz evaluations, which is pretty funny. If you want even more pictures, we can actually also do image processing now, which is very cool. So this is just a basic, 3x3 mask blur. But so we can sweep this, I don't know, say over posits. Again, we have on the horizontal axis, we have bit cost. We have then structural similarity between the image that we're computing in the reduced number system versus the reference number system with 32-bit posits. So here's my reference input image, which I stole from Halide. We can see that if we use a high precision reference, this costs us 4 billion Titanic bit cost. But if we go down to lower precision, we can save a bunch of those bits, but get increasingly broken posit quantized images. So anyway, hopefully Tensors will help you as much as they've helped me. It's definitely been a huge boon to have this when porting applications over to use with Titanic. I hope that having this functionality will greatly expand the set of benchmarks that can be included in FPBench. Contributions are of course welcome. Please go on GitHub and submit any if you have them. For people who are more interested in using tools, I hope this will also help us to expand the set of domains that the tools are actually interesting for. So obviously, tensor support is already available in Titanic, in my tool, which is available on the web. And also, it's pretty well supported in the FPBench sort of reference tools. Hopefully, it will spread other places as well.